Welcome viewers, this is a part 5 video of design of warehouse structures. In this we are going to apply the crane loads, SLS load combinations, ULS load combinations, and we are going to do the design of a member size for various columns like main column, wind column, door column, rafters, and finally we are going to do the deflection check for all the model. So let me look into that load applications for crane first. Generally, this crane load details applying to the robot structural model, we need the data sheet of the crane manufacturer. But however, we are assuming here some values here, like we are going to consider the 60 kilonewton or 6 ton capacity of the crane. So that should be applied, that should be having a two wheels. We are going to have as a concentrated loads, which is having a 3 ton or 30 kN on each wheel at 500 mm distance from the center line of the axis. So it means that both the wheels are having a 1 meter spacing, and the moving spacing also we are considering as a 1 meter interval. So this we are going to apply on the robot structural model on either beams on left and right side of the building. So let we see the model. So here you can see that model which we have earlier done, and we have applied all the loads except the crane in the previous part. We need to highlight this, we need to hide this cladding so that the crane beams is visible clearly. Go to loads, special loads, moving. So we need to create a new load. So these are the BSEN and Euro by default. They are as a vehicle loads, which is applicable for the bridge design. We are not going to design a bridge, we are going to apply the crane load on this. So we need to click this new, and we can create a crane, click OK. So as we see in that, we are having a concentrated force on two wheels of the crane, each is having a 30 kN, and one wheel is having a minus 0.5 meter distance from the center of the axis. So you can see the picture here also. And the second wheel is also a concentrated force having a 30 kilonewton, having positive 0.5 meter. So both the wheels are 0.5 meter away from the center line of the axis. So this is what the load we need to create. Click add. So you can see the crane which we have created, the load case is added here. Now we need to apply on the left side crane beam first. So we can type here crane left. We need to create the root. Click this define, select line, select the first point of the beam and select the second point of the beam. So you can see the root is defined already here now, 147. So now we need to fix this step. So we are going to tell that this is going to move by 1 meter once. So the every load is going to transfer at a 1 meter interval. So we are, if we want, we can also reduce this 1 meter to 0.5 meter, but the analysis part will take more time, depends upon the step or interval between the moving. So here that load directions we are going to apply only the vertical downward load. So this load direction definitions axis will be 0 for x and 0 for y and minus 1 for z. So now we can click this apply. So you can see that there is a green line highlighted here. So it means the moving load is applied to this beam. Now we need to apply the right side of the beam. So here we can directly edit the new name as right and define the path by clicking this define and line. So this beam start from 147 to 153 mode. So now you can see there is a new route is created, and these are similar like left side beam, and click apply. So you can see now this beam also created a screen. So now after this, click this calculations. So now this calculation analysis is done. Now right click to display the moving loads. Click here loads, go to moving loads, tick all this value and click OK. So select the load left 23 load cases. So you can see the moving load which is applied here, and right side load you can see here the load. So we need to find out where the other wheel load cases. So for that, click this select component. So the location is somewhere here. So we need to adjust this location so that we can able to see the moving load. Also click result, go to this diagrams of members. So select this MY, click apply, so that you can able to see the movement also. So now we can also see that animated view. Click animation, so you can see the moving load with respect to that bending moment also changing. So we can also save this. So this is our video we saved. So this is what about crane load applying to the model. Now next we will look into that load combinations applying to the model. These are the load combination calculation Excel which we have seen in our previous video. So in the right hand side you can see that various definitions and the lines which we have developed in order to make it this load combination to copy and paste into the robot structural model. So these are the load cases for SLS and ULS category 1 and ULS category 2, which are arranged here, and with so this column is a load case, first one, that is the permanent load, and these are the factors which is applied with respect to the load combination factors, that is first case is self weight, and the second case is the second column is about the factors which is to be multiplied for the self weight, and this one is a leading variable, and these are the factors which is to be multiplied with that, and finally this is a accompanying variable or leading variable. Something here in the wind load calculation there is some changes are there, so however it is interface with the interchange with the leading and the accompanied variable loads, but these are the load combination and the factors. So once this load types are assigned, then we need to pick from that load type which are the type we have assigned for which load category. Say for example for self weight we have assigned in our model as load number 1, so that load number 1 we need to consider here. So similar like for imposed load on roof hitch we have consider as 2, and for crane load, so for crane load we need to consider both left and right side in different separate load cases. So as you see that our crane load case we can find it from here. So you can see while selecting this load case 23, it is showing the load value and the load magnitude. So and if you are selecting the 24, then it is going to show the right hand side. So this is what we need to change here, and we need to add it here as a 23 as a first left side load combinations load case, and the 24 is a right side load case. So this is what accordingly the wind we used to have 7 to 10 number as a external coefficient and 11 and 12 are internal coefficient. You can see here that 7 to 10 is a external pressure and 11 and 12 are internal pressures. So these are the load case we have added here into that load combinations. So now it is easy for us to create the load combinations in robot structural model. Let we see how it is going to do. So go to loads. First create the manual combinations. So you can type 101 and this you can keep it as a SLS. No need to edit here, just click OK. And here in this window you can able to see that load combinations which is added here 101. Simply close this and go to loads, click combination table. So this combination table, in that click go to the tab edit. So now we can just copy and paste this cells into the robot structural model so that the n number of load combinations can be pasted here. For that you need to keep here. So you can see all the load combinations is added here. So until 570 is there, because this is self combined from the robot structural model itself due to the crane loads. So the crane loads are you can see here while we are going to apply the moving load 23 and 24. So then this case also again redistributed into crane loads from 17 to 20. So this load cases are by default generated by the robot structure based upon the load movement and the load distance which we have assigned already in the moving load definitions. So accordingly this calculation, this load combination also get increased without to our expected load combinations, because we have calculated that the SLS load combination should be in up to 191 starting from 101. So there are some 90 number of load combinations we have assigned, but robot by default it is considered from up to 570. So next we need to apply the SLS first category load combination. So for that we can consider the load case from 601. As you can see that SLS load combinations is occupied up to 570 numbers as per robot model itself. So we can close now this, and again we need to create the same method which we have done. So go to the loads, click manual combinations, and here click new, and in this ULS you can directly type 601 and click OK. And now again you can close this and go to the combination table. Click loads combination table, so that this load combinations we can copy and paste here. So here from 601 is the ULS load category is starting in this robot model. So we can directly copy this all the load combinations along with the load factors as we have defined in the Excel and paste it into that from selecting this entire row of 601. So that again here also this will assign some according to the moving load we defined, it is going up to 866 of the load number of combinations. So as per this our calculation it should be coming only 653, but due to this robot by default application of various load combinations it is increased. So now again we need to add some 901. So similar like we need to do for same thing for the ULS category 3. You can close and again reassign this. So now again this ULS category 2 also we are going to copy and paste into that. After this row 901. So now all the load cases are assigned here. So however the load combinations is going to get increased in the robot structural model. Again this analysis part also will take more time. So now we have applied all the loads and all the load combinations into the model. Next stage is we need to analyze this load and load combinations along with the model, and we need to design the member size. So for that after assigning all, we want to click just the calculation. So now after completing these calculations, and next we need to go to the design of members. For that click design steel member design. So in that we need to select from this member list, select members all, so that all the steel members can be selected, and just copy this and paste over here in the member verification tab, and also this we need to click it, and you can click all the SLS load, whichever the load case is applicable here, and run calculation. So it will take more time as we are having many members and many load combinations. So after this our result will be like this, and all our members are passed here. So here you can see that section members and sizes, which is showing as okay means it is passed, and also you can see that slenderness and usage ratio, which is within the limit, as the ratio utilization ratio is having less than 1. So after that, if you want, you can also take the detailed report and simply report full report, that you can take it and you can submit along with the calculations. And finally we also need to check the deflection of the members, and which is to be within the limiting value. So you can see for this, in order to find the deflection, go to the results and click deflections diagram for members. So this will provide you the deformation. In the left hand side you can see the deformations, and click exact deformation of members, and click these parameters to view and click apply. So as we know that what are the load case which are applicable for SLS, that we need to select. So here some 22 and up to 87 we can just type it. 22 to 87 are SLS case which we have seen. So according to the selected serviceability SLS load combinations, we need to find out which one is having the maximum deflections. So accordingly we need to check with our codes what code is stating. So for example, so this on the screen you can see that a PDF file SCI P399, which is a design of a steel portal frame. So here you can see that a lot of deflection limits is provided. For horizontal deflection at the eaves, we need to consider for fiber reinforcement sheeting, or so here our case is applicable for this profiled metal sheeting, so which is stating this horizontal deflection should not go beyond h divided by 100. H is a building height from up to the eaves. So that definitions and all we can able to find out from here. Also the vertical deflections is stating that the profiled metal sheet should have some b by 100 and or less than or equal to b square plus s. So these definitions are given here in this material, so that we can use to check that. Generally we can do like comparing these maximum deflections with the height divided by 150. So that is we found sufficient. So for height, if we are assigning as a 12 meter, then 12,000 divided by 150, we generally used to have 80 mm. So as you see that 33 mm, which is more less than the 80 mm, even the utilization and deflection factor we can less than 50% we are having. So this entire structure model is passed in deflection also. So that is what the member design to be done. Look description for more related videos and subscribe to this channel for more updates. Thank you.